Hi, my name is Yoni Talitman. I am a principal embedded software engineer working at Northrop Grumman. Welcome to the Vector Symposium. In today's presentation, we're going to take a look at an approach to achieve DO-178C 331 conformance in large-scale Simulink modeling environments. So today we're going to review the structural coverage analysis required by DO-178C. We're going to take a look at really what DO-178C tries to achieve from us by leveraging the structural coverage requirement, and we're going to see how VectorCAST is able to achieve that objective through its native tools. When using model-based engineering, challenges can arise when attempting to conform to DO-178C, specifically when obtaining structural coverage. We're going to take a look at Simulink, see the verification workflow, and then see how VectorCAST, using the VectorCAST Simulink toolbox, is able to mitigate those structural coverage challenges across development environments. DO-178C states, and I quote, that the analysis must determine which code structure, including interfaces between those components, was not exercised by the requirements-based test procedure. DO-178C isn't just interested in a unit test against one component. It wants us to view the software holistically across all file elements that comprise the source code. The analysis has to correlate to the appropriate design assurance level of the software. There is DAL A, B, and C, each with its respective objectives. In our case, we're analyzing structural coverage. This analysis has to be performed against either the source code, the object code, or the executable object code. And the analysis has to confirm that via requirements-based testing, that data and control coupling is satisfied between software components. Specifically, control coupling relates to how one software component influences the execution of another component, while data coupling relates to how data is transferred between the components. So the key takeaway is that DO-178C really wants you to focus on the totality of your software. It's not interested in just how one piece works. It wants to see how that one piece works within the overall software environment. So how does VectorCAST satisfy the structural coverage requirement? So VectorCAST supports requirements-based tests. These are tests that are written against your standard requirements. It supports range testing. These are just normal range testing from value A to value B against some unit under test. It supports robustness testing. These are tests that test out of range values, such as not a number, infinity, etc., etc. It supports data and control coupling tests. These are tests that determine the coupling relationship between different software components. And we can see here on figure 1 that the source code is contained within that box to a collection of UUTs, units under test. VectorCAST will take one of the source codes, it will create a harness around one of those units, and it will allow you to test it. The culmination of that process includes code instrumentation, which satisfies the structural coverage requirement for DO-178C. But notice that the source code is all within a singular development environment. If you were to have a project, let's say something in Visual Studios, for instance, that comprises of C or C++ code, you're within a singular development environment. You selected a piece of source code from that environment. You've given it to VectorCAST. You've written tests against it. That code has been instrumented, and the results of that are against the unit. And VectorCAST, at this point, has no issue aggregating coverage upward across those different software components because they're in the exact same development environment. And we see that here. So in a standard hand-coded environment, your source files aren't going to differ from the main development environment. You're going to have a collection of files. Those files are all included in a build process. The files are written in hand code, so they come from the same source, and VectorCAST is able to operate on that. A software environment, however, that utilizes model-based engineering tools now creates a detached environment from your overall software project. So what this means with respect to Simulink is you have one set of code that is written by hand, whether it's C, C++, or otherwise. You then have a model-based auto-generated code that originated from a completely different environment. We have MATLAB and Simulink. It's a separate IDE. It's a separate ecosystem. And the question that we have to ask ourselves, and that DO-178C begs us to look at, is how are we able to see the relationships between those software components, even though they span different environments? And this is the question that at the end of this presentation, we're going to be answering. Before we can answer that question, we need to take a look at what a verification workflow looks like within a Simulink environment. So we're going to take a look at how testing is performed against the Simulink model throughout its lifecycle. At the very beginning, we always start with requirements. Those requirements are written, and a software developer will take those requirements and translate it into a Simulink model. At this point, we perform what's called model-in-the-loop testing. This is testing that verifies the accuracy of the requirements against a model during its early development. At this stage, we haven't left Simulink yet. We're still within the MATLAB Simulink ecosystem, and we're using those tools as they're presented to us. In order to verify that the actual auto-generated code, however, is accurate with respect to its structural coverage, we need to perform what's called software-in-the-loop testing. This is where the auto-generated code is taken, it executes on our host computers, and because that code is instrumented, we go ahead and obtain coverage results. The very last step of a model testing workflow is what's called processor-in-the-loop. Processor-in-the-loop is where the auto-generated code now needs to be cross-compiled and executed on the actual target processor. And this is intended to reveal faults caused by the target compiler or even by the processor's architecture. We can take a look here at the images to the right that VectorCAST is actually able to integrate within the SIL-PIL environment. It goes ahead, instruments the code. For SIL, for PIL, what we do is we take that auto-generated code, we don't instrument it because we want to run it against the requirements, and we run it against our target processor. In the next slide here, we're going to take a look at exactly how VectorCAST is able to integrate within SIL or PIL. So in our case, within the SIL environment, we're going to show how the VectorCAST Simulink toolbox is able to collect code coverage against the auto-generated code. This toolbox, developed largely by Jaime Segura of Vector, takes the model-based test vectors that were created originally for the modeling environment. It takes the model itself, generates code against that model, instruments the generated code against the requested coverage level. The same model test vectors, once more, that were created for the MIL environment are tested against the model's auto-generated code, and then at the conclusion, VectorCAST is able to output the functional and code coverage results associated with that test. We can see on the right-hand side of the presentation, the aggregate coverage report is exactly what we would expect for a unit test environment. This is no different than what we see using VectorCAST unit, C, C++, and we've essentially shown that VectorCAST Simulink toolbox is able to achieve code coverage results against an individual Simulink model. And it's able to leverage, via the native behavior of SIL and PIL, the exact same test vectors that were created for the modeling environment. But now we have to ask ourselves the original question of the presentation is, how do we take those two development environments, the one that was written in hack code and the one that is executing within MATLAB and Simulink, and merge them together in order to, once again, satisfy that DO-178 objective of finding the relationship between software components within the overall software environment. A software environment that utilizes conventional hand code testing, and a software environment that uses model-based development and tests. And this is where the power of VectorCAST really shines. If we take a look at the image on the screen here, we see the VectorCAST Simulink toolbox in action. This is where the auto-generated code belonging to a model has been instrumented, and that coverage has been imported into our VectorCAST project. We then take a look at a unit test environment. This is an environment that was written using the VectorCAST unit C++. It was written against requirements, and once more performed within the VectorCAST project file. We then have another file, a top-level file, that we went ahead and tested using VectorCAST QA. We collected the coverage results from that process, and once more imported that into our VectorCAST project file. And here's really where things shine. We're able to take the totality of those coverage results, aggregate them upwards into a holistic report, and find what DO-178C has been seeking from us since the beginning, the relationships between those different software components, even though they're across different development environments. What this allows us to do is to satisfy those DO-178C objectives that we discussed at the very beginning of the presentation. While VectorCAST satisfies the DO-178C objectives natively, the VectorCAST Simulink toolbox essentially has created an ecosystem for us to verify these objectives against both hand code and modeling environments leveraging Simulink. We can see that MCDC is achieved throughout development environments, decision coverage is achieved throughout development environments, statement coverage is achieved, and more importantly, the same for data and control coupling, which now reveals the relationships between the unit tests that we've written and the models that we've developed. I hope you've enjoyed this presentation. I hope you've seen how the VectorCAST Simulink toolbox, integrated within VectorCAST itself, can obtain the structural coverage requirements that DO-178C needs from us, and I look forward to answering any questions you may have.